All right, so let's continue now. So the purpose of this example is that, you know, every LP problem, regardless of whether it's in standard form or not, can be converted into an equivalent LP problem in standard form. So one last observation is the following. So we can solve the equivalent LP problem. Equivalent LP problem in standard form. In standard form, instead of the original problem. So in other words, rather than solving that problem, I can solve instead this problem. And once we have an optimal solution, which I'm going to call x1 bar, x2 prime bar, x3 prime bar, x3 double prime bar, s1 bar, and e1 bar, we can recover an optimal solution for the original problem by well, for example, what's the value of x1 star in the original problem in terms of the decision variables of this problem? So we haven't changed x1 at all, so x1 star is exactly equal to x1 bar. Okay, so basically the value of the first decision variable here would be the same as the value of the first decision variable over there, right? What about x2, the value of x2 in the original problem? Well, we have this relationship, right? So if this is true, then x2 should be minus x2 prime. So I'm going to multiply the second decision variable by minus 1. Okay. What about x3 star, the value of x3 in the original problem? So it's going to be a difference of the third and the fourth decision variables, basically. So the value of x3 star will be given by x3 bar minus x3 double bar. And that's about it. So the first decision variables, sorry, the first problem had only 3 decision variables. So I can get the values of those decision variables in terms of the values of decision variables in this problem, basically, okay? What can I say about the optimal value of this problem and that problem? Exactly. So the optimal values are the same. So that's important. So whatever optimal value I have here will be the same as the optimal value over there. So the optimal values are the same. So as I said, this is a really important result, actually. It's very simple, but it's important. So basically, it means that, for example, if you want to write an algorithm, okay, using a computer code, then you can only write your algorithm for LP problems in this form, because every LP problem can be turned into this form, okay? So as a result, the user can give you any LP problem in any form, but you can always convert it into an equivalent LP form, equivalent LP problem in standard form. As a result, your algorithm can only work with this type of problems, for instance, okay, which is perfectly fine because every problem can be turned into that format, okay? So that's important. As I mentioned, from now on you can assume that your LP problem is already in that form, because if it's not, you can always put it into that form, okay? So which means that the standard form LP problems are quite general, basically. They include every LP problem you can think of, okay? And indeed, for example, in your projects, when you sort of use the Excel solver or the Express solver, the solver first takes your problem and first puts it into this form and then solves this problem, okay? And once it has a solution using these relations, it actually sort of recovers the optimal values of the original problem, and it reports you solutions in terms of your original variables. But behind the scenes, essentially, it's first taking this problem and turning it into standard form and solving that problem instead, okay? Is that clear? So essentially what this means is the following. So my goal is to solve the original LP problem, right? Okay. So what I'm saying is that instead of solving this problem, I'm going to solve this problem instead. Okay? And once I have an optimal solution of this problem, then using these relations, I can actually obtain an optimal solution for the original problem as well. So instead of solving this problem directly, first I'm converting it in this form, then solving this problem, and from that solution, obtaining a solution for this one. Okay? So, this is my original problem. This is the problem in standard form. So first I'm taking this route, then I'm having the optimal value, then I'm actually getting the optimal solution for this problem as well. So, any questions? Other questions? All right, so there's one more thing that I want to mention. So, similarly, a maximization problem can be converted into a minimization problem, converted into an equivalent minimization problem. And you can also do it in the other direction, and vice versa. We have seen this before, but I'm going to just make this more formal, basically. So suppose that your problem is as follows. It's a maximization problem. You want to maximize x1 minus 2x2, subject to x1 plus x2 is less than or equal to 1. And x1 and x2 are both non-negative. Let me just quickly draw the feasible region. So this is a constraint corresponding to, this is the region corresponding to first constraint. Then we have non-negative to x1, x2. So our feasible region is given by a triangle, right? Okay? Now we can solve this problem graphically. So what does the isoprofit line look like? So if I set x1 minus 2x2 equals 0, it's going to go through 0, 0. I need one more point, so if x2 is 1, for instance, x1 will be 2, right? So it's going to go through 2, 1 as well. So essentially, so something like this. So as a result, this is the isoprofit line. So this is the line corresponding to x1 minus 2x2 equals 0. So this is a maximization problem. What does my improving direction look like for this problem? So it's going to be 1 minus 2. I'll just look at the coefficient of my variables. And 1 minus 2 actually looks like this one, this vector right here. And since this is a maximization problem, I should actually move in that direction as far as I can. And what's the optimal value? The optimal solution? Well, if you move along this direction, it's not too hard to see that this will be the optimal solution. So my x star will be given by 1, 0. And the optimal value, what's the optimal value? If you plug in 1, 0 into the objective function, you get 1, right? So as a result, the optimal value is equal to 1. Now, how can I turn it into a minimization problem? So we discussed this last week. So I can multiply the objective function by minus 1, right? And if I do that, then I'm going to get the following problem. So I'm going to minimize minus x1 plus 2x2, subject to same constraints. x1 plus x2 is less than or equal to 1. x1 is not negative, x2 is not negative. Let me just draw the same feasible region once more. So now, since this is a minimization problem, I'm going to look at the iso cost line, right? So I'm going to have minus x1 plus 2x2 equals 0. So what does that line look like? So I have minus x1 plus 2x2 equals 0. Well, it's exactly the same as this line, right? Right? So x1 minus 2x2 equals 0 is the same thing as minus x1 plus 2x2 equals 0. Okay? So as a result, I'll have exactly the same line. So this is the line corresponding to minus x1 plus 2x2 equals 0. Now what does my c vector look like for this problem? So now it's going to be minus 1 and 2, right? So minus 1 and 2 actually now points in this direction. So this is my c vector, minus 1 and 2. Okay? But since this is a minimization problem, I should go in the opposite direction of c, right? And if I go in the opposite direction of c, what's the best I can do? Well, I should move in this direction. And the best I can do is, not surprisingly, the same point over here, right? So x star is still equal to 1, 0. What's the optimal value in this case? What's the optimal value of the second problem? So I get minus 1 basically, right? So I just plug in 1, 0 into this objective function. So I get minus 1. So this is something that you have to be careful about. So whenever you convert a minimization problem into a maximization problem, you have the same optimal solution. So the optimal solutions are the same. But the optimal values are the negations of one another. Okay? So basically, if you have 1 in the original problem, then the optimal value will be minus 1 in the other problem. Okay? So as a result, when you do this conversion, please pay attention to the optimal values. The sign of the optimal value will change. Okay? The optimal solution stays the same, but the sign of the optimal value changes. And if you think about this a little bit, this is not too hard to see because I'm multiplying the objective function by minus 1, basically, right? So I get 1 in the first problem, then obviously I'm going to get minus 1 in the second problem. Okay? Is that clear? So as a result, you can turn every maximization problem into a minimization problem by multiplying the objective function by minus 1. However, the optimal values also change signs. Okay? So that's important. The optimal solutions are the same, but the optimal values will have different signs. Okay? Any questions? Is that clear? So is the last example clear? Give me some reaction. So, yes. Okay, good. All right, so now we're going to start talking about systems of equations, okay? So this is one of the reasons why linear algebra is a prerequisite for this course, because we're going to use that information. But just to sort of recall some basic things, we're going to start discussing solving a system of equations. Here's my first example. So suppose I have 2x1 plus 2x2 plus x3 is equal to 9. Then I have 2x1 minus x2 plus 2x3 is equal to 6. And finally I have x1 minus x2 plus 2x3 is equal to 5. So I have 3 unknowns and 3 equations. So what I want to do is I want to find values of x1, x2, and x3 that satisfy all of these equations at the same time. Okay? In other words, I want to solve this system for x1, x2, and x3. And you've seen this before, right? So you know how to solve this. Now, one way to express this system is as follows. So I can define a matrix A, okay? And my A matrix will be the coefficients of my variables. So the first row will be 2, 2, 1. Then I have 2 minus 1 and 2. Then I have 1 minus 1 and 2. So this is going to be my A matrix. Then I'm going to define a vector x given by x1, x2, and x3. Then I'm going to define another vector b. And b will be given by the right-hand side values, 9, 6, and 5. And if I define my a, x, and b in this way, then I can express this system in what way? So a times x is equal to b, right? Exactly. So basically, this system and this formulation are equivalent. Okay? It's not too hard to see that they're the same. So if you multiply a and x, you multiply the first row by the first column. So you have 2x1 plus 2x2 plus x3 is equal to 9. And that's exactly your first equation, and so on and so forth. So you've seen this before, right? So Okay. So how do we solve this system? Well, so we set up the following tableau. So I'm going to start with 2, 2, 1, and the right-hand side is 9. So I'm just sort of removing the variables from the system, from the picture. 2, minus 1, and 2, the right-hand side is 6. Then 1, minus 1, and 2, and the right-hand side value is 5. Okay? So I guess sometimes you actually put this as well, right? So what do we do? Well, we try to turn this into canonical form, right? So we do sort of Gaussian elimination, right? So how does that work? Well, I'm going to start with this coefficient right here, okay? And I'm going to try to turn it into 1. How can I turn it into 1? Well, if I multiply the first row by 1 over 2, for instance, or divide it by 2, then that component will be 1. So I have the following, x1, x2, x3, and the right-hand side. So I have 1. Then what's the second coefficient in the first row? 1 again. Then I have 1 over 2, and the right-hand side is 9 over 2, basically, right? Then what do I do? Well, I want to also turn the other coefficients in the first row, in the first column, to 0, basically, right? So I want to actually replace them by zeros. So how do I do that? Well, I can multiply this row by minus 2 and add it to second row, basically, right? You've seen this, right? Okay. So if I multiply this by minus 2 and add it to second row, what do I get? Well, the first term becomes 0. What about the second term? I have minus 2, minus 1, so I get minus 3. Okay. What about the third one? So I get minus 1 plus 2, so that's going to be equal to 1, basically, right? And what about the right-hand side? So I'm going to multiply this by minus 2. I get minus 9 plus 6. So I'm going to get minus 3, basically, okay? Then I'll just do the same thing for row 3, okay, the third row. So what am I going to do? Well, I'm going to multiply the new row by minus 1 and add it to the last row, basically. And if you do that, you have the first component is 0. What's the second one? You get minus 2, okay? You get minus 1 over 2 plus 2 becomes 3 over 2. And what's the right-hand side value? So it's going to be minus 9 over 2 plus 5. So that's going to be 1 over 2, basically, right? Okay? So now the first column is exactly in the format that we want it to be. Okay, there's only one non-zero coefficient, and that's equal to 1. And all the other coefficients are equal to 0. Then I'm going to move to the second row and second column. So I'll just do the same thing for this one now, right? So this is going to be my next pivot, right? So what do we do? First, again, I'll just try to make it equal to 1. And then I'm going to try to make every other non-zero coefficient in that column equal to 0, okay, by using elementary row operations, right? So that's exactly what you did earlier. So let's just do that quickly as well. So my new tableau looks like the following. So first, I'm going to start with the second row. I'm going to divide everything by minus 3. I have 1, minus 1 over 3, and the right-hand side is 1. So now I'm going to try to zero out these two terms, right? So I'm going to make this one and this one 0. So to make the first one 0, I'm going to multiply this by minus 1 and add it to the first row. Okay? And if you do that, you have 105 over 6, and the right-hand side becomes 7 over 2. Then similarly, I'm going to try to make this term equal to 0. And to do that, I'll multiply this by 2 and add it to the last row. And if you do that, you have 0, 0, 5 over 6. And the right-hand side is 5 over 2. So now, again, the second column is exactly in the right format, right? I have 1, 0, 0. Did I make a mistake? Okay. All right, so now I'm going to move to the third row and third column. So I'm going to try to make this equal to 1. Okay. And then I'm going to try to make other terms equal to 0 by using, again, elementary row operations. And if you do that, you have x1, x2, x3, and the right-hand side, you get the following. So 1, 0, 0, right-hand side is 1. 0, 1, 0, right-hand side is 2. And 0, 0, 1, right-hand side is 3. So what's my solution for the problem? So x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3. So essentially, the point of doing these elementary row operations is the following. So this is the system that you started with, right? This is your AX equals B system. And that system is actually equivalent to this system, right? Instead of solving the original system, you may as well solve this system. And of course, the nice thing about this system is, it's straightforward to solve this system, right? So x1 is already equal to 1, x2 is equal to 2, and x3 is equal to 3. So essentially, the main idea behind these elementary row operations is actually start with a sort of general form of system of equations and turn it into something much simpler in some sense, okay? But of course, when you do this, you still have the equivalence. The solution to any system is the same as the solution to the original system, basically, okay? And once you have this in this final form, you can just read out the values of your variables, okay? So x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3. And if you recall from linear algebra, so this is system of equations in canonical form, right? So essentially, we start with any arbitrary system, and we put it into canonical form. And the sort of nice thing about canonical form is that I can get the values of my variables directly from this system, okay? So we have x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3. Now, one thing that you should pay attention to is the following. In the final tableau, in the final form that we have, every column has exactly 1, 1, and everything else is 0, basically, right? In the first column, I have 1, 0, 0. In the second column, I have 0, 1, 0. And in the third column, I have 0, 0, 1. The second observation is that, the 1s are in different rows, right? So in each row, there's exactly 1, 1, okay, on the left-hand side. So as a result, this form is called canonical form, right? So as I mentioned, the idea is that, so once you have such a system, you turn it into an equivalent but much simpler system of equations. And from this one, you can get the solutions immediately, basically, okay? So as a result, one way to think about this is the following. So any solution to this system is also a solution to this system, is also a solution to this system, and is also a solution to this system, and vice versa as well. So any solution to this system also solves this system, and this system, okay? So in other words, 1, 2, 3, 4, these 4 systems are equivalent to one another, okay? If you gave me any of these systems, then I would have obtained the same solution, basically. Okay? All right. So let me give you another example. So once again, everybody knows this, right? So, right? Okay, good. All right, so the second example. So let's say I have x1 plus 2x2 plus x3 is equal to 4. I have x2 minus x3 is equal to 1. And 2x1 plus 6x2 is equal to 9. So suppose now I want to solve this system. Okay? And I'll just sort of play the same game, right? So I'm just going to do this quickly. So I have x1, x2, and x3 on the right-hand side. So the first row reads 1, 2, 1, and the right-hand side is 4. Then I have 0, 1, and minus 1. Right-hand side is 1. Then 2, 6, 0. Right-hand side is 9. Okay? All right, so I'm going to start with the first pivot again. It's already equal to 1. And the second row already has 0. I just need to deal with the third row. Okay? So I just need to zero out this entry, basically, right? So this is to be 0. And how do I do that? Well, just multiply this row by -2 and add it to the last row. And if you do that, you have 1, 2, 1. Right-hand side is 4. The second row stays the same, 0, 1, -1, 1. And if you multiply by -2 and add it to the last row, you get 0, 2, -2, and 1. So now we took care of the first column, right? So what's my second pivot? Well, I'm going to move to second row and second column, okay? So this term is already equal to 1, but I need to zero out the other entries in the second column. So I'm going to multiply second row by -2 and add it to first row. I'm going to multiply the second row by -2 and add it to the last row as well. And if I do that, I have the following. I get 1, 0, 3, right-hand side is 2 for the first row. 0, 1, -1, right-hand side is 1. Then 0, 0, 0, right-hand side is -1. Okay? Well, so this is going to be my next pivot, but the problem is that that is equal to 0. Okay, so I cannot actually continue pivoting. Now, what does that final system say? There's no solution, right? Why is there no solution? Because essentially, if you read this in terms of equations, so 0 times x1 plus 0 times x2 plus 0 times x3 has to be equal to -1, right? And that can never happen, so the left-hand side is 0, right-hand side is -1, so which means that this system has no solutions, okay? And since all these systems are equivalent, then that implies that this system has no solution either, okay? So row 3 basically reads 0 times x1 plus 0 times x2 plus 0 times x3 is equal to -1. So this implies that there is no solution. Does everyone see why there's no solution to this system? Okay. I'm going to give you one last example. I know this is kind of boring, but just sort of give you an idea of what might happen in general. So I'm going to use pretty much the same system. X2 minus x3 is still equal to 1. 2x1 plus 6x2, instead of having 9, I'm going to have 10 on the right-hand side. Okay? So let's again try to solve this quickly. So I have x1, x2, and x3, and the right-hand side. So I'll have 1, 2, 1, and 4. Then 0, 1, -1, and 1. And 2, 6, 0, and 10. I'll just play the same game again. So I'm going to start with the first pivot. The second row is okay. The third row should be zeroed out. So you have x1, x2, x3, and the right-hand side value. We get 1, 2, 1, 4. Then 0, 1, -1, 2. Sorry, 0, 1, -1, 1. And 0, 2, -2, and 2. Okay? So now I'm going to look at the next pivot. So this is my next pivot. So I need to zero out the other entries in the second column. And if you do that, you end up with the following. You have 1, 0, 3. The right-hand side is 2. 0, 1, -1. The right-hand side is 1. And the last row reads 0, 0, 0. And the right-hand side is 0. So once again, if I look at the third column and third row, I have a 0 entry, so I cannot use this as a pivot. Okay? Now, what does this mean? So essentially, now if I look at the last row, so row 3 in this case reads 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 0. And that equation is not hard to satisfy, right? Okay. So in particular, regardless of what the values of x1, x2, and x3 are, that equation is always satisfied. Okay? So this implies that the third equation basically is already implied by the first two equations. Okay? So whenever I satisfy the first two equations, then I automatically satisfy the third equation as well. Okay? In other words, the third equation does not bring me an extra constraint or an extra restriction in some sense. So as a result, we say that the third equation is redundant and can be removed from the system. Okay? So in other words, another way to think about this is, whenever I satisfy the first two constraints, then I automatically satisfy the third one as well. Okay? Whenever I satisfy the first two equations, then the third one is already satisfied. So as a result, the third one does not give you any new information in some sense. Okay? So which means that if I simply get rid of equation number 3, then nothing changes in my system. Okay? So I still have the same set of solutions. So my question now is the following. So how many solutions do I have for the example number 3? So why infinitely many? Well, so let me start with an easy case. So one solution is as follows. So I can simply set, for example, x3 equals 0. Now, if x3 is equal to 0, what can I say about x1 and x2? X2 is 1, and x1 is equal to? Just look at the last table over there. x1 is equal to 2, basically, right? So essentially, just look at this system right here. Okay? If x3 is 0, then x2 should be 1, and x1 should be 2, basically, right? Okay, so this is one possible solution, and indeed, if you plug in 2, 1, 0 to the original system, you will see that everything is satisfied. Okay, so the question is this the only solution? Well, as you said, the answer is no. The question is, for example, how can I find other solutions to this system? So one way to think about this is, I can think of x3 as a parameter in this problem. Okay, so what I can do is the following. So I can let x3 be equal to lambda. Okay, where lambda is any real number. Okay, then if this is the case, what can I say about x1 in terms of lambda? 2 minus 3 lambda, right? So if you look at the last table, so you have 2 minus 3 lambda. What about x2? It's going to be 1 plus lambda. So as a result, I have the following system. So I have my x, which is given by x1, x2, and x3. And I can write it as follows. x1 will be equal to 2 minus 3 lambda. x2 will be 1 plus lambda. And x3 is just lambda. I can also write this as 2, 1, 0 plus lambda times minus 3, 1, and 1. So I'm just separating the lambda terms and the constant terms. Note that 2, 1, 0 is the same solution as we have over here. So in other words, 2, 1, 0 corresponds to choice of lambda equals 0. But for every different choice of lambda, I get a different solution. Okay? For example, if you set lambda equals 1, you get, I don't know, minus 1, 2, and 1, and so on and so forth. Okay? So which means that since there's a solution for every value of lambda, there are infinitely many solutions to this system, right? So this implies that there are infinitely many solutions. All right, so we have seen three cases so far, right? So the system may have a unique solution, which was example number 1. The system may have no solutions, or the system may have infinitely many solutions. Okay? So as a result, we can have the following summary. So the system X equals B where A is an m by n matrix, X is an n-dimensional variable, and B is the m-dimensional right-hand side vector. So here I'm allowing that number of equations and number of variables can be different from one another. Okay? Belongs to one of the following three cases. So case number 1, Ax equals B has a unique solution. So there's only one X that satisfies this system. Case number 2, Ax equals B has no solution. So in other words, the system is inconsistent. Okay? And case number 3, Ax equals B has infinitely many solutions. So as I said, I mean, you should have one of these three cases. You have either no solution, or you have a unique solution, or you have infinitely many solutions. So you can never have a situation where you have two solutions, for instance. Okay? So number of solutions can be either equal to 0, or 1, or infinity. Now, if you think about this a little bit, so there's kind of similarity for the number of optimal solutions as well, right? So, we can have 0 optimal solutions, or 1 optimal solution, or infinitely many optimal solutions. So there's an analogy between number of solutions to this system and number of optimal solutions. So in the last 10 minutes, I'm going to just mention some facts from linear algebra. So fact number 1, the system Ax equals B has a solution for every choice of B if and only if and you fill out the rest. So I'm giving you a system Ax equals B, and number of equations and number of variables can be different. Okay, so I'm just talking about general system. It has a solution for every choice of right-hand side vector if and only if. Sorry? Well, so I'm talking about the rectangular matrix, right? So as a result, in general, rectangular matrices are not invertible. If A was a square matrix, you're right. So, for a square matrix, A has to be invertible. What about the general case?
Less than unknown.
Number of equations less than unknown. So, what do you mean exactly? If and only if the system has no bedrock. What's a bedrock?
0, 0, 0, 0.
Now let me just go back to this example.
We call it backwards.
So for example, this is an example where there's no solution, right? Okay. And I'm starting with this system. So this is my A matrix, okay? And after elementary row operations, I obtain this system right here, right? So now just consider this part, okay? So which is my reduced matrix, basically. Now, how many linearly independent rows do I have in this? So I have only 2 of them, right? Okay. So which means, what's the rank of this matrix? So the rank is the number of linearly independent rows, basically, right? Okay. So the rank is equal to 2. So what about this matrix right here? So what can I say about the rank of this matrix? Well, it's also equal to 2, basically, right? Because essentially, we obtain this matrix by using elementary row operations, and elementary row operations do not change the rank of the matrix, right? So it does not, you do not affect the rank of the matrix. So the problem is that here you have 3 equations, but the rank of the matrix is equal to 2. Okay? On the other hand, if I go back to this example, here I also have 3 equations, but the rank of this matrix is always equal to 3. Okay, so which means that, regardless of what the right-hand side value is, there's always going to be a solution here, right? Whereas right here, in order for this system to have a solution, the right-hand side of the third component should be equal to 0. Okay? So what can I deduce from these sort of discussions? Well, basically, this statement's true if and only if there are no redundant rows in my system. Okay? So if and only if my system does not have any redundant equations, okay? And that's the same thing as saying that if and only if the rank of A is equal to m. So the rank of A is the same as the number of rows, okay? So A has m rows. For example, in this case, the rank of A is equal to 3, which means that if I change the right-hand side, okay, then for any right-hand side, I will always find a solution. Okay? Whereas in the second example, for that right-hand side, there's no solution. Okay? So as a result, if the rank of the matrix is the same as number of rows, then we always have a solution. Okay? And this is true for every right-hand side B. Okay? So independently of B, I can always find a solution. Yes?
What I wanted to say was the number of equations, if the number of equations equal to number of unknowns.
Okay? No, it's not the same thing though, okay? So here we have 3 equations and 3 unknowns, but still there's no solution. It's not just about the number of equations or number of variables, okay? Sure, yes. So once again, now I'm talking about a rectangular matrix, okay? So A can have, let's say, 2 equations and then, let's say, 4 unknowns, okay? So, and if you don't have a square matrix, there's no determinant, basically, right? So determinant is only defined for square matrices. So here I'm just talking about general system. I may have 2 equations and 4 unknowns, for instance, okay? Because that's the kind of systems that we're going to be interested in LP problems, for LP problems, okay? So as a result, for every choice of P, there's a solution if and only if the rank of A is equal to M, which means that all the rows of A are linearly independent, basically. Okay, so that's the same thing as saying that. The second property is that if AX equals B has a solution, and if the rank of A is less than M, then that means that the system contains redundant equations. In other words, A has linearly independent rows, A has linearly dependent rows, which may be removed from the system, which may be safely removed from the system. So what does that mean? So suppose that AX equals B does have a solution, but the rank of A is less than M. Okay, so what do I know? I know from the first part that that system cannot have a solution for all right-hand side vectors V. It can have a solution for certain choices of P. So in this case, then there is always a redundant equation, which means that there's always a linearly dependent row, and I can simply safely remove it from the system without changing the solution. So this is the case in example number 3. So here we have a situation where Ax equals b does have a solution, okay? But the rank of A is still equal to 2, okay? So which means that we have 3 equations, but the rank of A is 2, which is strictly less than 3. Then there's this redundant constraint, which is the third one. I can always get rid of that. And that does not change the system, okay? So that does not change the solutions in my system. Okay, finally, now when does Ax equals b have no solution? So Ax equals b has no solution if and only if now let me just go back to example number 2 again. Now, what is the rank of this matrix? It's equal to 2, right? What's the rank of this larger matrix? It's equal to 3, basically, right? So the rank of the larger matrix is equal to 3. There are 3 linearly independent rows, whereas in the smaller matrix, there are only 2 linearly independent rows, okay? And this is exactly what the this is the cause of the problem. So if this rank of the smaller matrix is less than the rank of the bigger matrix, then there's no solution, okay? For example, if I go back to this example, the rank of this matrix is equal to 3, and the rank of the larger matrix is also 3, basically, right? Because there are 3 rows, you cannot have rank more than 3. And if I finally go back to this example, the rank of this matrix is 2, and the rank of this larger matrix is also 2, basically, right? Okay? So the problem arises whenever the rank of this matrix and this larger matrix are different from one another, basically. Okay? So as a result, the system has no solution if and only if the rank of the matrix given by A augmented by B is strictly greater than rank of A. So once again, essentially, this matrix has the same rank as the original matrix, basically, right? A augmented by B. So whenever the rank of that matrix is strictly larger than rank of A, then there's no solution. Okay? So one last observation. So, for example, if the rank of A is equal to M, okay, then that inequality can never be satisfied. Right? If the rank of A is equal to M, then that inequality can never be satisfied. Why is that? What is the largest possible value of rank of A augmented by B? It's equal to M, basically, right? So, or it cannot exceed M. So as a result, if rank of A is already equal to M, you can never satisfy that inequality. Okay? So everything is tied in together, basically. Okay? Any questions? So I'll see you on Thursday.